yeah, this is physics. It's going to be a good year. It is going to be a good year. Today is the 17th, 2020. And we're going to start off by talking about what physics is. So I'm a biologist by training. Physics was the last thing I ever expected to teach. Biology, yeah, I wanted to teach biology. Chemistry, yeah, I could do chemistry. I never thought I'd teach physics. And I remember a really snotty physics major in college who was harassing biology majors by saying, well, you know, I like to do things with my science. Shut up. But it is often said that biology is more descriptive, and chemistry and physics are more predictive. I don't know that that's strictly true. But, you know, while there's tons of overlap between the physical and the biological and the earth sciences, physics really in a lot of ways is at the base of a lot of stuff. So if you look at biology, chemistry, physics, biology is what? Chemistry is how. Physics is why. Literally, and you know, we're not going to talk about it, literally at the atomic and molecular scale, physics is driving why things work the way they do. So the chemistry is how it actually works. The biology, we can describe what's happening, you know, but yeah, physics underlies it. So that's the really exciting, fun, cool, you know, like cocktail party part of physics. We're not going to do any of that. Sorry. My goal for my physics students has always been to get you ready for the first year of college physics. And generally that first year of college physics is broken down into three main areas. You do classical mechanics, that's sometimes called Newtonian Mechanics. That's that first piece. And Newtonian Mechanics is bodies in motion. It is velocity and acceleration. It's the classic, basic, boring stuff. Hasn't changed since crazy Isaac Newton was sticking his fingers in his eyes. It includes forces and work. That is all classic mechanics. Not to be confused with quantum mechanics, which is the sexy stuff that we don't talk about. That's Einstein. And that's like particle physics and subatomic particle physics. We don't get there. We don't do it. That is the stuff that makes you popular at parties. Mechanics never made anybody popular. It just made them cry. But it's okay. You'll all be crying together, and maybe with hot chocolate. So that's mechanics. We focus on that. You will be very well grounded in basic mechanics going forward. Thermodynamics is something that we're not going to do. It's how I would love, oh my gosh, my dream is to have my physics kids build solar hot water heaters and, you know, do actual like thermal constants and do heat transfer. It's not in the Ohio standards. It doesn't really get you ready for your first year of physics. So it sounds like a whole bunch of fun, but yeah, we're not going there. Thermodynamics is how heat is exchanged in systems. And it's really tough. A former student of mine who went on to, I think he ended up doing mechanical engineering at Akron. And he was a brilliant kid. I mean, he got B's in physics without cracking a book, which is crazy. I think he failed thermodynamics. First, he had to take it twice. And he said, like, I've never failed anything in my life. And his mom said, well, yeah, welcome to thermodynamics, you know. It's tough. And your book treats thermodynamics. It's got a chapter on thermodynamics, which is obviously handled at a much lower level. It's interesting stuff. If you want to dip into it, dip into it. Go build a hot water heater at home. Send me pictures. But we're not doing it. Vibrations and wave phenomena is one of the other areas. This one I used to cover, and I've largely sacrificed. And I will tell you why. So you've had some vibration and wave phenomena stuff in physical science. This is light and sound and mirrors and lenses. Of the three areas of physics that I want you to be ready for your first year, this is the easiest one to walk into and pick up pretty fast. Mechanics is nearly impossible to do that, and I think the electromagnetism, it pays you dividends to have some of that up front. So if I have to sacrifice one of them, what I sacrifice is the vibrations. They cut sound out of the Ohio standards for high school physics, so we don't do that. And I could sacrifice electronics to get some lens stuff in, but it's not worth it. So that's probably the other part that if you're taking, now for those of you who are going into engineering, you're going to take more than this, but for those of you who are not engineering majors, like biology majors, your first year of college physics is going to be mechanics, vibrations and wave phenomena, and typically electromagnetism. So optics and wave phenomena are related. Optics is really where your lenses are. That's what we used to do. But again, we sacrifice that for getting to a little bit of electromagnetism, getting to Coulomb's law problems, getting to doing some basic circuit stuff. Even though you probably had some circuits in physical science, is that correct? Okay. But I can tell you that you didn't have charged particles and forces of attraction between them. So that's something that it's beneficial if we can get you a little bit of that. Relativity and quantum mechanics, like these are the cool parts of physics, and we don't get to do them at all. Relativity is all the Einstein, time travel and the cool stuff. Every now and then I have a kid who comes, like an English major kid who comes back and says, I took physics at Kent. Which one? 7 ideas that shook the world. No, you didn't take physics. You took cocktail party physics. It's the exciting parts of physics summed up conversationally. And then quantum mechanics, like I said. So here's the weird thing about mechanics and quantum mechanics. Kind of the central unifying idea in science is that the rules work the same way everywhere. That in our universe, in some other universe in the multiverse, or some other collection of galaxies in the multiverse, in our galaxy, in another galaxy, in rural Ohio, or in the middle of Beijing, the rules work the same way. Objects accelerate due to gravity the same way. Friction works in the same way. Forces work in the same way. Predictable patterns of chemical behavior emerge. That the rules are the same, no matter how big the system, no matter how tiny the system. The problem arises in that at the subatomic level that seems to not be true. Oh, well, that stinks. So one of two things is possible. Either there are actually 2 sets of rules, which scientists really don't like the idea of, or there is one larger umbrella set of rules that makes things appear as though they're behaving according to 2 sets of rules at the microscopic or the subatomic level versus the macro level. Some of the things that attempt to answer those questions are things like string theory. And if you get a chance and you're looking for a geeky book to read, Brian Greene's The Elegant Universe is fantastic. And he is a physicist who works on string theory. And he's a neat guy. But there are all these like wild things that are attempting to answer why the rules look like they're different, because they can't be different. That's not legal. Toast, cinnamon toast. Okay, so on this chapter plan, you can see, we talked a little bit about the fields of physics. I would always recommend that your physics textbook is actually pretty darn good. It's well laid out. It does a good job. It's a little bit dated, but mechanics hasn't changed since Newton. So the fact that this book is from 1992, the clothes are pretty stupid, but other than that, it's solid. I always recommend that you read the section that we just talked about, and you can even read it in advance if you want. The homework problems are the pages should all be there. They're from the chapter PDF. We're actually going to walk through this video about models, because what I want to tell you, and this kind of gets to more of what general science is, but also physics. Typically the people who I get in physics tend to be pretty sciencey, pretty science-minded. So I think it's a good place to have the conversation about the fact that there's not one scientific method. And it drives me absolutely crazy because in the middle school, and it's a reasonable thing to do at the middle school level. You know, we don't teach things the same way when you're in 5th grade as we do when you're in 8th grade as when you're in 12th grade, and we shouldn't, or we're doing you a disservice. But in middle school, you learn that there's the scientific method, and it's this step, and then this step, and then this step, and there's the scientific method song, and I think it's on, yes. My daughter knew it from Magic School Bus. And it's a reasonable approach to take at that level. But what we very often fail to do is that when you get a little bit older and you can handle a little bit more complexity and subtlety is talk about the fact that there's not one method. That there are a set of methods and ways of thinking that are important in science, and it's not a linear cookbook path, that it's actually like a crisscrossed maze that all comes back to very scientific ways of thinking. So it's based on observation. It has to be objective and it has to be factual, and that's foundational for any science. You know, whether we're talking life science, earth science, physics, chemistry. And it seeks to explain the method that we use for explanation is hypothesis. So you probably at some point learned the definition of hypothesis as an educated guess. That is so bogus. But it's a reasonable way, I guess, to talk about it at a younger level. A hypothesis is a working explanation. So hypotheses seek to explain how something works. There are things for which there aren't any good hypotheses. There are lots of things for which there are competing hypotheses. And, you know, we'll talk about, well, the leading hypothesis for this is. You know, the other hypothesis for this is. And it's through the process of testing that we attempt, well, Brian Greene, the physicist I just mentioned, is quoted as saying, I've been working on, and this was a few years ago because I think he's nearing retirement now, I've been working on string theory for 30 years, and every morning I get up and I try to break it. He is attacking the hypothesis for explaining, and yes, it's called string theory, but we'll get into theory and hypothesis later. You know, he is attacking and attempting to break the very thing that he's been working on by testing and seeing if he comes up with a test that is inconsistent with that model. Hypotheses can also be described as a model for how something works. A model can serve as a hypothesis. Once we've got data, you know, in any science, we interpret that data. We evaluate, we examine, we comb through, we organize that data, and it's from that interpretation and evaluation that we can actually come to conclusions. So I thought it was really interesting. And I hadn't thought about it in this way. I forget who it was who was recently quoted as saying, you know, part of the issue that the public is having with coronavirus science is, you know, well, they keep changing. Well, they keep changing what they're saying. That's how science works. Science is a continual process of testing, drawing in new information, reevaluating conclusions, finding new things, and the public isn't used to seeing the process. And, you know, we're all kind of living the science right now. I mean, you and I are all parts of a large-scale experiment to see if we can get a bunch of humans into buildings together in the winter. And, you know, anyway, these are some of the methods associated with science. Now, what science very often uses in that organization and putting together data, models aren't what you think. So models are useful in experimental design because models can serve as a way to sort of bring a hypothesis into the world. There was a book I read years ago. It was by a guy who did climate science, and he talked about, I forget where he was teaching, and he had this very excited undergrad in his class who came rushing up to him and said, because this guy had worked on like a preeminent climate model, like one of the big ones. And this undergrad who was so excited said, can you take me to see the climate model? And he's like, oh, well, no, because it's a piece of software. You know, it's a piece of software that posits that this is the way the system works, so if you change this, then this should change in this way. That's a model. I mean, we have physical models, which are what we think about most often. You know, and you've worked with physical models like globes and skeletons and stuff. Verbal models can just be an explanation. Visual models could be a map. It's those mathematical models that we work with most in physics. And years ago, I worked on a project at YSU, and they were bringing high school kids in who were interested in various science fields and running through a summer program. It was pretty cool. And the engineering department had one that was rapid prototyping and testing. This was before there were 3D printers in a whole lot of places, and the kids got to 3D print a design of an object. Well, then they got to model stresses. So they had a 3D scan of the object, and the mathematical computerized model simulated what would happen when that object was interacting with its environment, and you could see where the stresses in the object would be. Oh, you know, your teacup looks really cute, but that handle's going to fall off the third time anybody picks it up, because the model can predict that sort of thing. So models are important in terms of experimental design because they are an explanation. They kind of fit with hypotheses. Thought experiments, we're going to watch a video on. These are the ones that we do more in physics. You're familiar with the concept of controlled experiments. Some of you have done them and gone to State Science Day with them. Controlled experiments are those things where we've got a control group, we've got an experimental group. You know, we don't give the control group whatever the experimental group gets, and we see where it goes. That's why biologists love twins. Kidding, we don't condone human research like that. Okay, so, well, you know the joke. What did the biologist say when she had twins? Ooh, I've got a control. Anyway, thought experiments are useful for things where we cannot physically experiment. So some of that particle physics, the subatomic stuff. And we're going to watch the two videos from the chapter plan, and then you're on your own to do the homework. But the funny European guy is kind of nice. So if you're not here for this, you should watch the video.